So this short video will give you a hint about finding basis of null space of A from RREF of A. First, a little bit of theory. We start with A, m by n. We apply some algorithm to produce its RREF B, m by n. Then from property of RREF, we know that row space of A must be same as row space of B because we have done nothing but elementary row operations. Next, we shall use the result that for any matrix P m by n, the null space is nothing but the orthogonal complement of row space of P. Here I am working over the real field. It is quite easy to see why this result is true. Just think of P as a collection of its rows. Now, something is in null space of P means P times that vector is 0. Now, how do you get this 0? It is this row times this, which is basically dot product of the first row with that vector. That is 0, which means this vector, a typical element of the null space, must be orthogonal to the first row of P. Similarly, the second row of P is also orthogonal to this vector because of this 0. In this way, this vector must be orthogonal to all the rows. And this is, of course, vice versa. So, something is in null space of P if and only if it is orthogonal to all the rows, hence this result. Coming back to this, since we know row space of A is same as row space of B, if I take orthogonal complement of both of them, that will also remain the same, which basically means that null space of A is equal to null space of B. In other words, it is enough to find the null space of the reduced row echelon form, and that will be automatically the null space of the original matrix. What I shall now do is give you an example. I will take a matrix in RREF, which is of the order, say, 2 by 4. To create such a matrix, all that I have to do is to put certain ones, the leading ones, and the ones must always flow down towards the right. So I put a 1 here, and suppose I put a 1 here. Whenever I put a leading 1, I have to make sure that everything in that column is 0. So I have to put this, and since it is a leading 1, so I have to put a 0 here also. Now whenever I have a 0, I can put anything else here. So suppose I put the number 2, and since this is the leading one, these things may be just anything. Suppose I put the number 5 and 3. So this is a typical way by which I can quickly construct a matrix in RREF. Now we shall construct its null space in a systematic way, and from that we shall see a pattern. For a vector to be in the null space of this matrix, it must satisfy this equation. So A, B, C, D. Now, I have 1 and 1 here, the leading ones. As a result, I can express my variables A and C, the first and the third, in terms of the other two. Explicitly writing them as equations, I get these two equations. From these equations, we can write these two things. So I have expressed A in terms of B and D, C in terms of D. And how did I choose A and C? Because of these leading ones. They occurred in columns 1 and columns 3. So I could express variable 1 and unknown 3 in terms of the other two. Thus, any vector in the null space may be now written out like this. A, B, C, D. I have kept B and D as they are. In place of A, I have written this. In place of C, I have written that. So everything is now expressed in terms of B and D, which are perfectly free to move. Expressing these as matrix multiplication, we can write it in this way. Now observe that any value of B and D will give you a vector in the null space, and anything in the null space must be of this form. In other words, the null space of this matrix is just the column space of this matrix, and since we have reduced it as much as possible, so any arbitrary value will work here. So these two columns actually give me a basis of this null space. Now, if these two column vectors give you a basis of the null space, then I can take their negatives, and that will also give me a basis of the same space. So I have written them like this. Instead of minuses, I have put these things all positive, and these ones have now become minus 1. So basically, I want to produce these two columns as the output of my algorithm. Now notice the similarity between these and this. Observe that this part 2305 is precisely 2305, and think about it a little bit, you will immediately see that this is no coincidence. And also, look at their positions where they occur. They are occurring in those positions where I have the dependent things, namely in this case the dependent things were A and C, because we expressed A and C in terms of the other things. So this was for A, row 1, and this was for row 3. And these dependent things corresponded to precisely the columns where the leading ones occur. This part, they were just unaltered. B was left as B, D was left as D. As a result, here we just had a little identity matrix 1, 0, 0, 1, and when I negated, I got a minus identity matrix in place of all the remaining things. I have this minus identity. So from this you can understand I really did not need to go through all these computations. Just by looking at this, I can immediately write this down. Now think about this in general. Just take some other matrices in RREF form and see if you can utilize this pattern to immediately write down this matrix and implement that as a computer program, and you will get a way of obtaining a basis of null space of a matrix from its RREF.